Thanks to Brilliant for supporting today's video. Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today we're going to be working through an excellent cube colouring problem courtesy of Brilliant. Brilliant is an interactive online platform where you can develop your problem-solving skills across a variety of STEM subjects, but more on that later. The problem we are looking at today is as follows. We start with a 3x3 cube. So this will mean a larger cube made up of 27 smaller cubes. I'm going to attempt to draw this vaguely accurately. So a large 3x3 cube, which means we have 27 smaller cubes. Now each of these smaller cubes will of course have 6 faces. And we're able to colour those faces, again on the smaller cubes, one of 3 colours. So the faces can be R for red, G for green, and P for purple. And we're interested in possible ways of colouring these 27 smaller cubes. Now the 3 conditions that have to be satisfied are the following. Any colouring must be such that we can arrange the 27 smaller cubes into the large one where the outside is all red. So all of these outward faces on all of these smaller cubes all need to be red so that the whole outside of the larger one is red. But not only that, we also need to be able to rearrange the same cubes so that the outside is all green, and we need to be able to do the same just by rearranging so that the outside is all purple. So first of all, we want to know, does such a colouring exist? Can you do this so that the outside of our larger cube can be in all 3 configurations with the same setup for our initial 27 cubes? So first of all, is it possible? And then second, and this is the really interesting part, how many different ways can we colour our cubes so that this is true? So that could be 0 if it's not possible, but if it is possible, precisely how many ways can we colour our 27 cubes up to rotation such that we can satisfy this problem? This is of course quite a complex problem, and we're going to need to break it down into manageable steps on our road to the solution. The question here actually comes from the Brilliant course Contest Math 2, which is designed to help you to learn the skills required to tackle advanced maths competition problems. If you want to have a look for yourself before seeing my approach to the solution, head over to Brilliant where you can get started for free. And if you do decide to sign up, make sure you use the link in the video description to receive 20% off an annual subscription. Right, let's do this. Our first step to try to get a handle on the problem is going to be to try to convert it into something numerical. At the moment, there are a lot of moving parts within the setup. We have the large 3x3 cube, we have smaller cubes, they have faces, we can colour those faces. It's pretty complex. So as a very first starting point, what I think is going to be really helpful is actually to just simply count the faces. So we have 27 small cubes. Each one has 6 faces. So that gives us a total of 27 times 6, which is going to be 162 faces in total. So there are 162 small faces on those small cubes that we need to colour. Now, in order to satisfy the conditions A, B, and C, we need a certain number of those faces, all of the ones on the outside, to be red. We need the same number at least to be green, and again, at a minimum, the same number must also be purple. So here we have 1, 2, 3. We have 9 faces on a side for the larger cube. And there are 6 sides. So we actually have 9 times 6, we have 54 total faces on the outside. So let's call it 54 external faces. So in order to satisfy condition A, we actually need 54 red, we need 54 for condition B, and we need 54 for condition C. Now if you add up these 3 numbers, that gives me a total of 162, which is the same as the total number of faces that we have control over. So first of all, this suggests a problem might be possible. We do have enough faces that it could work. But it actually gives us an incredibly important piece of information. And it's something we're going to come back to again and again as we work through this solution. Because what this tells us is that we must have exactly 54 red, exactly 54 green, and exactly 54 purple. Because these were the minimum numbers required to make the outside one of these colors. And since the total of the 3 minimums is the total number of faces we have, these have to be the values. So what that means is when we have a configuration with all of the reds, let's say, on the outside, all of the reds as external faces, all of them must be used. So it's not possible to have a face that's red that isn't external. If A is going to be satisfied, all of the reds must be located on the outside of the cube. So all of the faces are used in the configuration. And as I said, that is going to be incredibly important. So I'm going to make a note over here to say all faces must be used. And we're going to see this come back time and time again. Now, let's look at the different roles one of our small cubes can play in the 3x3. So for example, if we look at a corner piece, and I'll do these in orange, up here, then a corner piece is actually going to have 3 visible faces. So we can see it more clearly perhaps on this one. So 1, 2 on top, and 3 here. This will also be a corner piece up here. This is a corner piece. And then we're going to have another 4 along the bottom. So in my picture, that would be this one. That's going to be this one. The one at the back that I can't see, and then this one in the corner. So our corner pieces, of which there are 8, so let's make a note here, we're going to have 8 corner pieces. And in each corner piece, there are exactly 3 external faces. So 8 corners where we need 3 external, that's right, on the surface. Now, in terms of other different types of cube, let's look at the central pieces. So these ones here, and I'll do these in blue. So this one in the center of this forwards face, this only has 1 external face facing outwards, because all the others are hidden by its neighbors. And you're going to similarly get 1 over here, you're going to get 1 in the center up here, you're actually going to have 1 in the center of all 6 of our faces of the 3x3 cube. So this tells us there are 6, and I'm going to call these centers, and each of those have 1 external. Now next up, we have these pieces. I'm calling these edges, because these have 2. So you have 1 on the top, and then the 1 on the side. So 1 here, 1 going around there, 1 here, 1 around there, 1 here, 1 around the back, here, 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 here. This one around the bottom, this one around the bottom. Now, these are a bit trickier to count, but the way I like to think about it is if we take this front face, we've got 1, 2, 3, 4. We have the same on the far side here, So that gives us 8. And then we still need another 2 on the top and then 2 on the bottom, and that's going to cover everything. So there will be 12 of these edges, what I'm calling them, and these are the ones with 2 external faces. Now, we know the total number, remember, it's 27. And what we've got here is 8, we've got 26, which just leaves 1. Now, this isn't a mistake, this is correct, because there will be the central cube, the one right in the very middle of our 3x3, where nothing will be visible. And that's also going to be important. So our final point over here will be, I'm going to call this the one invisible cube, and that one will have 0 external. So this now tells us how our 27 cubes in a configuration must behave. Now let's think about possible color combinations. So for example, can I have a cube that has 6 red faces? Can I have a cube with 4 red faces and 2 purple faces? We want to try and have a bit of an insight into what combinations of our 3 colors are potentially possible. And the best way to think about this is actually to consider partitions of the number 6. For a given number n, a partition looks at all of the possible integers that can be added together to make the number n. So here we are interested in partitions of the number 6. And we actually have a further restriction, which wouldn't be the case in a general partition problem. Because here we can only have 3 different numbers. So for example, adding 6 lots of 1 wouldn't help because we only have 3 colors, not 6 available. So we want partitions of 6 with a maximum of 3 numbers, let's say. So which numbers add together to make 6 where we need 3 of them? We can start with 6 plus 0 plus 0. So that would be just 6 of one color, 0 and 0. We can have 5 and 1 and 0. We can have 4 plus 2 and 0. We can have 4 plus 1 and 1. We can go down to 3 plus 3 plus 0, 3 plus 2 plus 1, and then 2 plus 2 plus 2. So I think there are 7 possible 3-number partitions of 6. Now, which of these are actually possible for this particular problem? So what I mean by that is, do any of these contradict anything that we've worked out so far on the board? And the answer, of course, is yes, they do. So this first one, having 6 of a single color. Now let's suppose we had that. Suppose we had a cube with 6 red faces. Now, we've said that there are 4 possible types of cube. We've got the corners, which have 3 external, the centers that have 1, the edges that have 2, and the invisible one in the center. So our 6 faces that are red, it's got to be one of these 4, because that's the only possible configuration of where you can position that cube. Now, we also said, and again I told you this was important, that all faces must be used. So if we have 6 red faces here, the best we can do, the absolute best we can do, would be to have 3 of them external, putting it in a corner, but then we have 3 unused red faces. They'd be facing inside. So that would mean our maximum we could get on the outside would only be 51, and therefore the whole cube could not all be red. So this actually cannot happen, because if it did, again, there would have to be some internal facing colors that were red, green, or purple. For the same reason, we actually can't have 5 of a single color, because again, at least 2 of them would be internal faces, and that cannot happen because all of them have to be used. So we can cross that one off, And again, we can cross off the 2 with 4 because we don't have a single cube that has 4 external faces. So the only ones that are actually possible are going to be 3, 3, 0, 3, 2, 1, and 2, 2, 2. And of course, these can be any combination. So 3 plus 2 plus 1 is the same as 1 plus 2 plus 3, where you're changing the number of each colour. We don't mind that at this point. We will get to that shortly. Now we know the type of colourings which are possible. Let's try and work out the number of each of these 3 cases. And we're going to start with the 3 plus 2 plus 1. And I'm going to underline that 1 because this is what allows us to work this one out. So for example, let's suppose I have a single face which is red. Now, over here, we know that all the faces must be used. So when I try and make all of the external face of my large cube red, this single 1 red has to be a part of that because we only have 54 and they all have to be used. So that must be one of these 6 central pieces. And in fact, it absolutely has to be one of those 6 central pieces. All 6 of them have to be a cube of this type because none of the other combinations have a single face of 1 colour. So in order to make this work and use all of the red faces, we're actually going to need 6 cubes that have a single red face. Now, 3 and 2, we can have 3 green, 2 purple, 3 purple, 2 green. That doesn't really matter at this point. We just know there must be 6 cubes that have 1 red face so that we can use them as the centers when we try and make the whole cube red. And the same thing will actually hold for the green. So the entire argument I just went through, it holds if I have a cube with a single green face. That must be used for the external green colouring, has to be one of those central pieces, and there has to be 6 of them. So we must also have 6 green and likewise 6 purple. And since it's not possible to have a single red with a single green, because that would mean 4 purple and that's not allowed, we in fact cover a whole 18 of our 27 cubes must have the 3, 2, 1 colouring. Now let's look at the 3 plus 3 plus 0 case. So 3 of one colour plus 3 of another and 0 of a third colour. And again, I'm underlining the 0 because the small number here is our way into this problem. Let's suppose I have 0 red faces. Now in the situation of trying to make the whole external 3x3 red, this one has 0 red faces, so it's quite useless. But what it means is it actually has to be our 1 invisible cube. It's the one right in the center, because if I put it anywhere else in the configuration, at least 1 face is visible, but it has no red faces, so that just simply doesn't work. So in order to make this possible, if I have a cube with 0 red faces, it will in fact have to be in the very center. So this is a single invisible cube in the situation of the external cube being red. Now if I replace red by green in that same description, if I have 0 green faces, this has to be at the center of the green cube, case B. And similarly, if it has 0 purple faces, it will be the central piece of case C. And there is exactly 1 such invisible cube in each setup. So in total, there will be 3 of these cubes, where 1 of them is made up of 0 red pieces, 1 is made up of 0 green pieces, and the third one is 0 purple pieces. For the 2 plus 2 plus 2 case, we could try to go through a similar argument, but we can simply just use the fact that we know the total number of cubes is 27. And we know that these are the only 3 possibilities in terms of the colour distribution. We've already said there are 18 of the 3 plus 2 plus 1, There's 3 for the 3 plus 3 plus zeros. So for the 2 plus 2 plus 2, that would leave us with 6 remaining. And then if we add together those 3 numbers, we get the total, which is our 27 cubes. Okay, final step. We now know the number of each configuration that has to be present in order to solve this problem. The last step is going to be figuring out what the specific colorings must be for each of these different situations. So if we start with the 2 plus 2 plus 2, so I can pick 2 red, let's say 2 purple, and 2 green. And if I went back and picked 2 green for the first 2, it's actually going to be the same. So no matter what I do, the 2 plus 2 plus 2 only has one possible combination, which is 2 green, 2 red, and 2 purple in some order. And we don't care about that order. So this one is already fixed. We need 2 red, 2 green, and 2 purple. And there is nothing else we can do. For the 3 plus 3 plus 0 case, we have to think a little more. Now, we made an important observation when we were looking at the 3 plus 2 plus 1 cube type about this single face of a certain color. So for example, if we have a single red face on the cube, we said there must be 6 of them. And then we said the same for green and purple, which gave us the total of 18 of this cube type. But picking a single red face means we have to pick either 3 green or 3 purple. And there's going to be 6 of those cubes. So ultimately, what this all means, putting this all together, is we already have 6 of our triples for both green, red, and as well actually for purple. So we have 6 of our possible corner pieces for each color out of these 18. Now over here, we said there were going to be 8 corners for each color. So if 6 of them are already coming from here, and in fact have to come from here, then the final 2 for each color have to come from the 3 plus 3 plus 0 case. So what that is actually going to mean then, and I'm going to tick this because we have no choice here, we have to do this. What this is going to mean is that I can pick 3 red with 3 green, I could pick 3 red with 3 purple, and then I also need a 3 green and a 3 purple. So across those 3 choices, which matches the number we're allowed, we have 2 occurrences of a triple red, 2 occurrences of a triple green, and 2 occurrences of a triple purple. So those doubles plus the 6 we get for each colour from this lot, this particular combination, gives us those 8 corner pieces. Some of you may have noticed that so far in our solution to the problem, we actually haven't had any choice. Everything has been completely fixed, completely predetermined by the 3 conditions and the problem setup. That's why I added ticks to these 2. We couldn't do anything else in order to fulfill all of the requirements of the solution that were needed. Now in this situation, we do finally get a choice, and this is where things get very interesting. Now before we dive into considering the different cases for the 18 3 plus 2 plus 1 cubes, let's just take stock of the rules that we need to have satisfied. So for example, we know that there must be 6 cubes with 1 red. We also know there must be 6 cubes with 1 green, and there must be 6 cubes with 1 purple. Now we also, from our discussion here, know that there must be 6 cubes with 3 red as well, to get the other 6 corners to go with these 2 corner pieces here. And similarly, we need 6 that have 3 green, and we need 6 that have 3 purple. And of course, the total number of cubes must be 18. I think the best way to figure this out is to draw a table. So let's start by listing the possible configurations. So for example, if I take 3 red, then I have a choice for how to take 2. So let's take 2 purple, and that leaves 1 green. But then I could go back and take 3 red and take 2 green, and that would leave me with a single purple. So that covers all possibilities when I take 3 reds. Now, I could, of course, have taken 3 greens. So let's look at that case. So if I take 3 green, let's suppose I take 2 red, and that leaves me with 1 purple. Now, again, I can swap the red and the purple. So I could have 3 green with 2 purple and a single red. And then finally, I can take 3 purple, and there's going to, of course, be the same 2 cases. 3 purple, let's suppose I did 2 red and 1 green, or 2 green and 1 red. So that gives me 6 possible configurations, all supporting the 3 + 2 + 1 setup. Now, how many of each can we pick? Remember, there have to be 18 in total, and we also have to satisfy these rules around the number of singletons and the number of triples. Now, I think my approach here would always be to start as simple as possible and to see if that case works. So what I mean in this particular case would be to take 0 of this first configuration. So I'm picking, in some sense, an arbitrary number for this setup. And then following the rules, hopefully, we can logically deduce what must happen. Maybe there's a solution, maybe there isn't, but it gives us a starting point. And then maybe we can go back and change that starting number. So if we take 0 of this particular setup in row 1, then looking at our rule around the triple reds, we need to have 6 cubes with a triple red. So the only other option then is actually to take 6 in row number 2, because only the first 2 rows contain the triple reds. Now, we've got 0 single greens, but I need to end up with 6 of them. So that only appears in one other location, which is down here. So there has to be 6 of those to make that work. And now I also have 6 triple purples, and that's the exact number that I want. So I'm going to have to take 0 of this one, otherwise I'd have too many triple purples. But now I've got 0 single reds. There's only one other setup in row 4 that has a single red, so I'm going to have to take 6 of them to end up with my 6 single reds. And then that should mean, yes, I've got 6 triple greens, so I need 0 there. And that total is 18. So you can double check this, and I advise that you do. This particular setup, 6 of configuration 2, 6 of configuration 4, and 6 of configuration 5, this will satisfy all of these rules, and this will be our first valid solution to the original problem. Now I say our first valid solution because there was nothing special about me picking 0 at the beginning. It was just a simple case to try and get a foothold in the problem. So if we go back and now let's say I pick 1, another sort of arbitrary number. Of course I can't go above 6, we'll come to that. But if I try 1 here in that first row, now let's follow this through, and I will go through this one for you just to really make it concrete. Let's go through and see if we can get a solution satisfying these rules and therefore a valid solution, different valid solution to the original problem. So again, we've got a single triple red. I need 5 more, so I'm going to have 5 there. Now I've got 5 single purples, so I'm going to need 1 more in the single purple column. Now I've got a single triple green, so I'm going to need 5 more. That will be that one. Now I've got 5 single reds, so I need 1 more single red. And then I've got 1 triple purple, so I need 5 more triple purples. And 1 + 5, that's 6, + 6, that's 6, so the total is 18. And again, that second column satisfies all of these rules, and therefore is a second different solution to our original problem. We can continue in this way, going back and increasing the number that we have of this first configuration all the way up to a value of 6. We of course have to stop at 6 because if I had 7 of that first configuration, I'd have 7 triple reds, which would contradict the fact that I need to have exactly 6. So you can go through now and fill in all of the other columns, and we will end up with 7 different solutions, where each one is then actually fixed by the number you pick from 0 to 6 of this first configuration. So there you have it. There are 7 possible ways to colour the 27 cubes using 3 colours such that they can always be rearranged into a 3x3 cube of a single external colour. If you enjoyed this problem, I really do recommend checking out Brilliant for many more like it. And remember, the first 200 to sign up using the link in the video description will receive 20% off the annual subscription. Thank you everyone for watching. Please do remember to like and subscribe if you've enjoyed the video, and I'll see you all soon. Take care.